All right, class, let's try the last part of the video. So we had already talked about trying to have the money compounded many times per year, right? Infinitely many times per year. And we saw that this expression 1 plus 1 over n to the power of n, yes, as we make n get closer and closer to infinity, this turns into the number e. So we could easily transform this expression here into what we call the continuous compound formula. So the continuous, that 1 plus 1 over n to the power of n turns into e, and then still I have my principal at the front to the power of RT. So that's the continuous compound formula, and this is the one that we will mostly be using. So anything that ever grows continuously, it doesn't just have to be about money, right? A principal amount of money, but really anything. Bacteria, whatever it is, starting with an initial amount, growing at a continuous growth rate, or decaying at a continuous growth rate, R, right? We're using this formula. So, and as I said, that's the one that we'll mostly be using because we will only learn how to take derivatives of exponential functions with base e. By the way, let me just get back to this. I should also mention, now that we talked about e, oh no, we're gonna talk about it on the next page, sorry about that. Okay, so let's use this formula. It says if $4,000 now, so that's actually really the same amount from before, is invested in a bank account at an interest rate of 7% per year, find the amount in the bank after 9 years if interest is compounded continuously. Okay. So we're going to use the continuous compound formula. We also call this formula the PERT formula. It makes it easier to remember. So $4,000, the base is the number E. The interest rate is 7%, so 0.07. For 9 years, so we multiply this by 9, put all this in your calculator. You have an e to the x button on your calculator. So you're going to end up with $7,510.44. Okay, don't forget to attach the dollar signs to your answers. And here it is. So the point is, this is the most you can get with what? $4,000 you could start with, 7% interest rate, and 9 years, yes? So if we had it annually, it's $7,353. So as you see, the amount grew by, well, a little bit under $200, yes? But sure enough, $200 is $200. Okay, so let's try another problem. It says, Elisa opened a retirement account with a 7.5% APR, means annual percent rate or interest rate, basically. That's percent per year, yes. In the year 2000, her initial deposit was $13,500. So we already know that the principal is $13,500. How much will the account be worth in 2025 if interest compounds monthly? How much more would she make if interest is compounded continuously? So let's see monthly versus continuously. Now, if we compound the money monthly, then we have to use our initial compound interest formula. In other words, A equals P times 1 plus R over N to the NT. Okay, so that's the compound interest formula. So in this formula, what I'm going to do is I'm going to put 13,500 in for P. 1 plus 0.07. Monthly means how many times a year? That's correct. That would be 12 to the power of 12 times. How many years are we leaving the money in there? Well, from 2000 to 2025, that would be 25 years, yes? So put all this in your calculator, 13,500. Oh, that's 7.25%. I still had the 7% stuck in my head from earlier. So 7.25%. Put all that in your calculator and you end up with an amount of $82,247.78. Okay, so there's that. Now, how much more would she have made if she compounded the money continuously? What does continuously mean? Continuously means continuous compound formula. So we have to use the PERT formula every time we hear the word continuous compound. So we start at the 13,500 e to the 0.0725. So I turned the 7.25% into a number I can use. And then the time is still 25 years, so put that in your calculator and you end up with 82,697.53 cents. So definitely a little bit more, okay? All right. It says Jamal wants to save $54,000 for a down payment on a home. How much will he need to invest in an account with an 8.2% APR, so again, annual percentage rate, compounded daily in order to reach his goal in 5 years? So that's what he wants to have in 5 years. So what we have here is the amount, okay? We're gonna put that in the formula in a minute. Compounding daily means which formula am I going to use? Definitely not the continuous compound formula, but the compound interest formula that we talked about. Okay, so that's the one we have to use. Good. So he wants to save $54,000. So how much does he have to invest now? In other words, we're looking for the present value. So it's the P that we're missing. So I put $54,000 for A. 1 plus the interest rate is 8.2%, so 0.082. Compounded daily, there's 365 days in a year, so N is 365. To the power of 365 times, he wants that to be reached in 5 years, so the time is 5. Okay, put that in your calculator. By that, I mean this whole amount. So when you put this in your calculator, you'll end up with a 1.5069. So sure enough, to get to P, all I have to do is divide by this 1.5069. So the principal, what you should be starting with right now, is $35,838.76. So that's not too shabby, right? So you want to get, that's basically almost $25,000. That's basically almost $20,000 years later, right? 5 years later. That's where the 5 came into my brain. Okay, all right. So finally, the last part of it, we'll talk, as I said, yes, about the natural exponential function. But we want to make this comparison. What is a better investment? 6% compounded monthly or 5.5% compounded continuously? So we kind of want to compare apple to apples. Now, monthly, definitely I'm going to have to use the compound interest formula. Continuously, I'm definitely going to have to use the PERT formula. Okay, now what do I know? I know the interest rate, yes. So I know to put in a 5.5% in there. And then this one is going to be a 6%, yes, for that interest rate. Great. What else do I know? Well, continuously doesn't give me an N, but monthly means that I have this N value, yes. I am given the N value. Okay, so as you see, if I want to compare this, there's 2 big key factors missing. I'm missing a principal and I'm missing the time. Now, sure enough, if I want to compare apples to apples, all I have to do is pick my own principal and my own time. I just need to make it the same. And you can pick $1 and you can pick a year just to make things simpler. The point is, if you're going to pick $1, you won't really see all those decimal places that are growing. So I suggest picking an amount that's a little bit more than $1. And I don't mean 2. I mean 100 or 1,000, something that would move your decimal place a few places over. So I'm going to pick a year for the time. That's fine. But for the principal, just to see a few numbers in there rather than just one, I'm going to pick 1,000, okay, just to see a comparison. Okay, so I'm going to plug in these values. So A, in this case, is going to equal to 1,000. 1 plus R is 6%, so 0.06, divided by N is 12, compounded monthly, to the power of 12 times. We said, well, pick 1 for the year. So when you put that in your calculator, you'll get $1,061.68. Okay, so basically your amount grew by $61.68 in 1 year, yes? Okay, putting all this into the PERT formula, 1,000, E is E to the power of 0.055, right? That's the interest rate, the annual interest rate. And then we'll keep the time also 1 year. Put that in your calculator, and you'll get 1,056.54. Now, so clearly, which one actually grows more? Even though we said continuous compounds is more times a year, what really made a difference, infinitely many more times, right, than the monthly amount. But what made a difference really here is the interest rate. So the lesson learned is the number of compounds really doesn't make much of a difference. What really makes a difference is even just a tiny little bit more of an interest rate, right? If you should have the same interest rate, what's going to make a difference is a little bit more time left in there. So time, interest rate makes way more of a difference than the number of compounds per year. So in fact, yes, it turns out that this thing is better. So if we would have used the dollar, then what would you have seen? You would have seen that you get $1.06, and that's $1. And if you round up, that's 6 cents. So you wouldn't have seen a difference there. You would have gotten $1.06, because again, you only can pick 2 decimal places for the dollar, and that's $1.06. So you'd be like, oh, they're the same. But they clearly are not. So just picking a little bit higher principal made that decimal move a bit. Okay, so the natural exponential function is the one that we'll be dealing with really in the examples in our business calculus, and is the only one that we'll learn how to take the derivative of in section 3.3. So the natural exponential function is the exponential function with base e. Okay, so the base is this Euler number. Okay, that's it. So it has its own special name. It's got the base e. And by the way, we can change any exponential base into a base e. So I'm going to write this down. And many times, even though things might be doubling or whatever, we still are or tripling, where it has a base of 2.7 or 3.9 or 1.2. We like to turn those into an e-base, and then the interest rate is going to be at the top. So we kind of like to take any such formula and turn it into a PERT type of formula. So we can change any exponential function into one with base e. Okay, so the way we're going to do that is 2 to the x. How do I turn that into a base of e? Now, the x stays the same, right? So the exponent is going to be there, the variable, the time that's changing. All I need to do is take 2 and turn it into an 2 is e to the what power, okay? So you will find that out in the next section, 3.2. How am I going to change 2 into an e to the something? The secret is what that answer is going to be. It's going to be e to the 0.6931 something something. So I challenge you to put this in your calculator and see if you're going to get close to 2. It's probably not going to be exact because it's going to need a little bit more decimal places, but I'm going to tell you that it comes super, super close to 2. Okay, and we will find out in 3.2 how that works.